Let us have here another function and determine whether it's continuous for the given value of x. But this time, in comparison to the previous example, where c is specific, here we'll have x for x element of real numbers. It means we're going to check whether the function f of x, here f of x equal to 2x squared plus 1 is continuous for all elements of x which are real numbers. So unlike the previous example where we were able to locate a certain c, if you would like to review that, you can. You have our c is 0, so we're able to apply that in our situation. Here, it looks to be more generalized because x could be any value as long as it's a real number. Nevertheless, what we're going to do here is that we are going to use the definition. Of course, this is what we consider as a polynomial function, or specifically a quadratic function. And we know that quadratic functions are continuous on R, or generally, polynomial functions are always continuous on R. That would mean it would already fit here in our calculus concepts. But here, we're going to show again the proof of this using the definition. Let me write here the portion of the definition. I'm going to remove the assumption of A being a subset of R, and then the mapping of the function from A to R, because I would like to provide the needed portions of our proof. So we have here, if for every epsilon greater than 0, there exists delta greater than 0, such that if x is a point in A satisfying this inequality, or a distance of x and c is less than, that's a delta, then f of x minus f of c must be less than epsilon. So we would like to show this here. Of course, we will start with letting a certain epsilon be greater than 0 and locating the value of, or the representation for our delta. In the previous example, it's easier for us to look at that because we have a specific value for our c. Here, we might be assuming a certain more complicated process because we would like it to be generalized, and delta is really needed in order for us to continue until here. So for this, of course, we know our f of x to be this one, and since f of c is needed, we also have our f of c here, which is equal to since it's f of c, take note, it's f of c, hence it's not specific, the value is not specific for f of c. Okay, so we will be using here again similar thing. You will have here 2c squared plus 1. Okay, and then what else? C is not given, so c is still c. Okay, now my point here is, before we could start, just like in the previous examples, and together with the limits, proving limit theorems, we are going to have a short scratch work for us to be guided. The scratch work here is will help us to identify the correct process that will allow us to return to this intended goal, the goal here. So with that, let me try to place here f of x is 2x squared plus 1 minus here f of c, which is 2c squared plus 1 here. Okay, so absolute value less than epsilon. We will return to that later. Let's just simply look into the form of this. So you will have here 2x squared plus 1 minus 2c squared minus 1. Okay, still, again, we will return to epsilon later on. This is equal to, you will have 2x squared minus 2c squared, factoring 2. You will have your x squared minus c squared. And of course, properties of absolute value, you can remove that 2. And you will have absolute value of x squared minus c squared. Okay? Our goal is to come up with x minus c. In this case, c is not specific. So once we could look for x minus c, it's already okay because we can already assume that to be less than delta once we can locate the delta. So for some instances, you can actually simplify this x minus c and x plus c because this is a difference of two squares. So we will have here 2 absolute value of x minus c and absolute value of x plus c. This is already okay. However, we have here x plus c, and we have no way to determine that. In short, the goal here is we will be representing this with a certain expression that will allow us to convert it to x minus c later. And this is where it gets complicated. We are not yet on the proving phase, but we are this is very important step for us to really structure our process. Let me note this as an asterisk to return to that later. Now, help me with this. just for if we are going to assume, because we know that for a while we know that x minus c is less than delta, right? If we're going to assume that delta is equal to 1, you will have here absolute value of x minus c is less than 1. Okay, take note, delta could be any value, so it's just one assumption. It will give us a more important flow later on, so let's just stick to that. Our target is to come up with x plus c. Okay, so how do we make this x plus c in this form? Notice that if we are going to have absolute value of x, okay, absolute value of x here, we can rewrite this as absolute value of x minus c plus c, right? So we'll have that this is just equal to 0, so it's okay. Now my point here is when we group this, you will have to apply the triangle inequality. You can separate that x minus c and plus absolute value of c. This is the what we call this one, the inequality for the absolute value of x. Since we assume this already as less than 1, so we'll have here the absolute value of x is less than 1 plus you have here absolute value of c. Take note, our goal is this. Why do we need to approach this manner? Because you will see here that as you go back to absolute value of x plus c, okay, we can use here triangle inequality. You have absolute value of x plus absolute value of c. And absolute value of x is already indicated here. So in short, this is less than 1 plus absolute value of c plus absolute value of c, which is just equal to 1 plus twice absolute value of c. Now, we were able to have a simpler form of our x plus c that we can apply here. Okay? In short, this form, the asterisk earlier, that is twice absolute times absolute value of x minus c and times x plus c, which is all less than epsilon. Again, that's the item we're removing here. Okay? We will have here another form of our x minus c that will be paired with 1 as the possible value for our delta. And we would like to isolate x minus c here. As mentioned, you have x minus c is less than, you have your epsilon over twice times the absolute value of x plus c. But this is again indicated here. That would mean this is less than epsilon over twice times 1 plus twice absolute value of c. The point here is we have two possible values now for our x minus c. So we have your x minus c is less than 1 and x minus c is less than this. Why do we need that? Because again, we would like to come up with an expression for delta which is greater than x minus c. And what are those values? The values are both 1 and this expression, because this represents our delta. So delta could be the minimum between 1 and epsilon over twice. Sorry for that. Let me rewrite this, removing something else here to make it clearer. The minimum of the set containing 1, the first possible value for delta, and then this one here. So you'll have epsilon over twice times 1 plus twice epsilon, twice the absolute value of c. Now, finally, we have our delta. There exists delta. This is the time we can start with our proof. Yes, we can start our proof once we have established our delta. Let's start with letting epsilon be greater than 0. And since we're able to identify our delta, we are also going to assume that here, that's the purpose of our scratch work, so that we could actually declare our delta as part of the definition. So we'll have to assume that delta is equal to whichever will be the minimum between 1 and epsilon over twice the product, or twice the sum of 1 plus 2 the absolute value of c. Okay, so whichever would be acceptable, then it would be our delta. And since we had that, we can now proceed to the next part of our proof, satisfying. Okay, then if we'll have to do this, x minus c, take that our c here. Okay, so we'll have x minus c is less than delta. So x minus c, absolute value rather, would be less than any of these two. Okay, so we can just what do you call this one, leave it blank in the meantime because we have two possible values for our delta. But basically, as part of the definition, if this is less than delta, which would mean that all of the rest of the things here will work, okay, as we have here x minus c less than delta. I'm talking about the scratch work. So we can now proceed to, we have, okay, our goal is to show that this is true. The absolute value of the difference of f of x and f of c must be less than epsilon. But of course, we know this from our scratch work to be equivalent to this form here. We can use this form here if you would like to, or you can move forward and using the rest. But let's just simply use this so that we could structure our definition. 2x squared plus 1, that's our f of x, minus 2c squared plus 1, that's our f of c, which again, able to simplify to this form. We don't need to show the rest because we already had our scratch work. They are still equal to twice the absolute value of x minus c and the absolute value of x plus c. Take note, there should be epsilon later, so we can now proceed to any of these scribbles that we have used here earlier to come up with our final form of our proof. Okay, take note that once we used here x plus c, we actually had x plus c earlier, this one here, less than, take note of that, less than 1 plus twice the absolute value of c. So once we use this equivalence, or I mean value, we will be changing the equality now to less than, okay? That's twice x minus c, and then you have x plus c is actually again 1 plus twice absolute value of c. That is for x plus c. Now, what would be our x minus c here, which would be used as part of our definition? Take note, x minus c is less than delta. So there could be two of them. It could be 1 or this representation for our delta. But nevertheless, let's look into this second form here, as we're able to identify already x minus c being less than this better form, which also resulted when using delta equal to 1. So let's use this final form here. So instead, you will have here again less than twice. Instead of x minus c, you will have this form, this one here, the other form for delta, that's epsilon over 2 times 1 plus twice absolute value of c, times again 1 plus twice absolute value of c. We're doing this because once we had that, we can cancel this, or let me use a different color here for my pen, and we also cancel this, leaving delta alone. In short, these are all, when simplified, equal to delta. So we have now shown that from this form, we have that is actually less than epsilon. That is actually the goal of this definition here. Okay, so we can write here, hence the absolute value of f of x minus the absolute value of the difference of f of x and f of c is less than epsilon. Again, per definition. So we now have our conclusion. Since epsilon greater than 0 is arbitrary, okay, then we conclude that what are we trying to show? What are we trying to prove? That this is actually continuous for all x element, x as real number. So we'll have here that f of x is equal to 2x squared plus 1 is continuous, pardon for the space, for all x element of real numbers. So with that, we are able to prove this already using the definition. Take note, this is how critical your scratch work is, so that you could actually guarantee the existence of delta as needed for our definition, and then later on use that to structure that this expression would be later on less than epsilon. Okay, this is how we show the continuity of this function for the given condition. Thank you very much for watching.